Hey everyone, we are the portable hydropower generator group for the mechanical engineering Capstone project under Professor Duva. Um, I'm Adam Walters,
I'm Brendan Bannon.
I'm Sungjin Park.
uh, and this is our design process for this project.
The problem we looked at was a lot of times when people go hiking and camping, their phone may die, and it's kind of important, especially if you run into an emergency. So we decided to create a portable hydropower generator that can work with dams. There's about 3,000 dams in Massachusetts, and a large portion of those are small dams that could fit with our project. And a lot of people can charge their phones if they take this design with them, this portable hydropower generator. We designed it to use a siphon to bring the water from one side to the other, and it would run through the turbine. We used flow simulation on a design multiple times to create the best design for RPM and flow rate, and some of the changes we made were with the piping and turbine.
Designed to run as intended. We chose to go with 1.5 to 2-inch PVC pipes for the frame. And other components we need are an electric generator that is capable of producing 10 to 12 volts, a voltage regulator to stabilize the voltage output to 5 volt, and a Kaplan turbine. Um, these are some pictures of our early concept drawings. At first, we weren't sure about which turbine to choose for our design, but we decided to go with the Kaplan turbine because since we are working with very small and specific values for our flow rates, height drops, and power, there's only one type of turbine that will fit for our specific need, and that is a Kaplan turbine. We were also not sure about how to get this device to get running, but we decided to use a siphon method since it's the easiest and the most efficient way for our design. These are the pictures of our finalized SolidWorks model. As you can see, we assembled the PVC pipes using PVC connectors and a 45-degree three-way PVC fitting for the inlet into the turbine.
When we first started, before we began to kind of test, we used those fluid equations in the center there in order to kind of get a estimated area of what kind of values we should be looking at and what we should be expecting. And we also used those values from the equations to kind of compare our simulation values to in the end to make sure everything was on track. We ran the flow simulation, and these are kind of some of the basic and best displayed plots that we got. On the left we have the flow trajectory, and you can see the velocity picks up when it hits the turbine and kind of changes direction, kind of following around the edges a little bit. And on the right is the cut plot of the velocity. We are working with extremely small velocities for this kind of project, so every small change and small difference in coloration mattered here. So after running many different flow simulations, we found that with this kind of design and this kind of limitations, we're working with very small RPM values. With RPM values this small, we need some sort of gearbox or stator or change in pipe diameter in order to actually get enough RPM to produce the kind of power that we are looking for. From these flow simulations, we learned a lot about the capability of hydropower, as well as the limitations of working with dams and drops this small. That is just about the overall explanation of our project. We'd like to thank Professor Duva for helping us through all of this, as well as Wentworth. And thank you for watching.